Hello, everyone. Come on in. It's actually time for class to start, but not everybody's here. So does anybody have any questions before we get rolling?
Sorry, can you hear me?
Yes, I can.
Okie dokie. I missed test. I think it was test 3. Yeah, test 3. I completely slipped my mind to do it, and I was
Okay.
wondering if I could get it reopened for a day.
Yeah, generally I just like take off 5 points if you miss it like that. So I'll open it back up for you. Yeah, see you missed 3. 4, you've got some time left. I can't remember what the due date is on 4, but I will definitely open it back up for you. You're not the only one. There's another student that has it that hasn't taken it as well. So someone might want to email me to remind me, but it's no big deal. Like I said, I work with you. 5 points isn't that bad of a deduction, but I have to do something because it's not fair. You had a little bit more quote unquote study time.
Yeah, no,
Uh,
I appreciate it.
no problem. I'll open it up and you'll have until is Friday enough time or you need till Sunday?
Let me look at my um Friday should be enough time.
Okay. I'll open up the practice test for that as well. So that way you can
Thank you
still
so
practice.
much.
No problem. Let's see here.
Professor Younger,
Yes.
did you ever get my email? Because I haven't taken the midterm yet because I wasn't able to last week. And I
Yeah,
sent you an email.
I saw one. Let me see. Actually, you know what? Yeah, that's what it was. I'm sorry. I had two students named Maya, and I now I know why she looked at me like I was
Oh.
So I evidently had a really wonderful conversation with a person you don't know who happens to have the same name as you.
Okay.
I'll send you an email after class with a plan for that. Okay.
Okay, awesome. Thank you.
All right. Thanks, Maya. Look at it. Crazy Mr. Younger. Oh boy. Anybody else have anything? All right, I'm making an exception for 2 of my peeps. And that should be ready to roll really soon. All right, that's made up. Anybody else have any questions while we're having all this fun? Fun stuff. Okay, now I want to do the practice test too while we're here, so don't forget that. This is that class. This is 242. Good Lord. Got that. All right, that's taken care of. So yay for me. All right, yeah, I'll remember to send you an email after this. Maya, let me write down your name because otherwise I will 100% forget.
I have a question.
Yes.
Is it too much to ask that the practice test stay open?
Yeah, the whole purpose of the practice test is I give you extra credit for taking it in preparation for your test. So if you're taking it after the test is done, then you're sort of defeating the purpose. And I look at it sort of like it's more like you're gaming the system because I give you extra credit for your highest score on that. But what I did in lieu of that was I made all the chapters available. So you can still go back and sort of just practice a particular chapter. You just can't practice that test. But to be honest with you, you still can. You can just do, the tests that are involved in it because normally my tests are the chapters that are involved with that test. because normally my tests are only 2 chapters. So like if you had a 25, 26 chapter test, then all you really need to do is the chapter 25 homework and the chapter 26 homework. So that's why I don't, that's why I shut it down the day that that your test is due. Actually, I do it like right about the same time as your test is due, just because I give you a lot of extra credit for doing it ahead of time. The only reason I do it is to try to motivate students to actually take the practice test. Rarely do I find anybody that does well in the class without doing the practice test beforehand. So I'm just trying to motivate them, even though they, you know, I would hope you'd be motivated as you are. You're obviously wanting to take it anyways, even though the test is already over. So do use the chapter test. They don't count against you or for you. And then, of course, use the other test too, because really the other practice test, when you go to, for instance, test 5, which would be the next one, or test 6, when you do that, that'll have a comprehensive portion of it. So you're constantly getting some occasional problems from earlier chapters, obviously in smaller numbers though. Anyone
Okay, thank
else?
you.
No problem. Is that Famada talking to me? I think it
Yes,
was.
sir.
Okay, I was just making sure. All right. So before I was, I don't know, I think I had a stroke or something and became Mr. Nice Guy and decided to help y'all with reviews for the midterm and all that stuff rather than keep it on covering material. Before that, we were actually in chapter 29 and we had began working with Lenz's law, which is a really neat conceptual law. Specifically, it's actually Faraday's law, but Lenz's law is sort of the part that makes the direction of the induced current make sense. And what Lenz's law says is that when there's a changing flux, a current will be induced in an attempt to basically undo that changing flux. In other words, if the flux is increasing, it's going to create a current that creates a magnetic field that tries to reduce the flux. And if the flux is decreasing, it creates a current that creates a magnetic field that tries to increase that flux. So by thinking about it that way, you can actually figure out, you know, for a given scenario, which direction is current going to be induced. And that's a big conceptual problem. It's, you know, such a good conceptual problem that I often put it in my hiring questions when I go to hire someone who claims to have a background in physics, or especially someone teaching physics. They should all know that. And I like it because it requires little, well, actually it requires no math. It just requires your understanding of a big concept that everyone should know, having completed a, you know, even a bachelor's degree in physics. So we're going to step off as if you guys still know that really well. By all means, you want to practice that as much as you can. Your book has a lot of practice problems for that. It has some in the conceptual portions for this chapter, chapter 29, and it has some in the, I think it's a section called questions at the end of the chapter. There's concept questions that appear in our chapter little test things that I put up. And then again, in the misconception questions, there's some stuff about it there. And then just the examples, and you can also look online for other examples. So make sure you're still up to speed with that. What I want to work with now is the other aspect of it, which is actually the calculations. And the calculations basically hinge on knowing the equations. So let me start off by sharing my screen, assuming that such a fancy thing can be done. Okay, it looks like it can so far. Yep, it works. Reality is reality, and all things are working. Woohoo! Okay. For some reason, it always throws my window way down the bottom, and I don't know why. Whoa, no. And it's got a size of the window that it prefers no matter what. I can't change that either. Urgh. Okay, well, good enough. So what I first want to talk about is what is Faraday's law? Well, what Faraday noticed was he had seen how, for instance, an electric field or a current can create a magnetic field, but he wondered if a magnetic field could create an electric field. So he tried all sorts of stuff, but luckily he was paying close enough attention one day so that he realized that though once you set up a magnetic field going through a particular type of wire situation or whatever, during that time, there was no electric field created or anything like that, or no current created from the magnetic field. But when he first turned it on and when he first turned it off, it did. So that was a really big thing to notice, because what he realized is it wasn't the fact that we had a magnetic field. It was the fact that the magnetic field was creating what we call a magnetic flux, and that the magnetic flux was changing. And when the flux changed, and only while it was changing, was there an induced EMF. So that's ultimately what Faraday's law found, is that an induced EMF occurs when there's a changing magnetic flux. So just for reminders, I want to write down what flux is in its most general form. And of course, that means I'm going to write it out in the most mathematical way possible. But basically, flux is, remember, sort of a counting of the number of magnetic field lines, or the fraction of magnetic field lines that go through, say, an opening perpendicular to that opening. So for instance, if you imagine a window, you can sort of think of, there's light that comes to the window and it comes at some angle with respect to the window. Part of the light ray is parallel to the window surface and therefore doesn't really light up very much. But another part of the ray, if you add them like vectors so that they give you the total ray at whatever angle the sun decides, well, that other part of the ray is actually perpendicular to the window surface, and that's the stuff that goes straight through the window. So in the same way, you can imagine a magnetic field going through any kind of closed or any kind of surface. What we do with that is we actually imagine a surface that spans to a boundary. And basically, you can create the boundary to be what you want. And then any surface that spans to that boundary is fair. So for instance, if you recall, probably when you were a kid, you had chances to play with bubbles, and they often had this ring you could stick in this little dish, and you stick it down and then you pull it like this. When you sit still, the circular disc would more or less have a sheet of flat bubble in the middle of the circle. But if you gave it a little pull, it would swell out behind and make like a sack looking thing. And if you spread it too far, it would just pop. But if you didn't spread it too far, you could make a fairly long bag-like structure out of the balloon. And every one of those structures you could make that are actually still tethered to the ring that you were using, or if you didn't use a ring, whatever shape it was, all of those are fair surfaces for that particular bounding curve. So that's what we're looking at with Faraday's law. And we say that the flux is a measure of the magnetic field that hits perpendicular to an area. And we define the dA vector in such a way that its magnitude is the magnitude of the area of the opening, but the vector A is perpendicular to the plane in which dA is defined. So for instance, if you're talking about a window of your house, the dA vector would point straight out of the house or straight into the house. And you know that when you take a dot product of something or of two vectors, then that's a way of finding the component of one that is parallel to the other. So since we define dA to be perpendicular to the surface, when B dot dA is complete, in other words, it's not B dA times cosine theta, in other words, cosine theta is 1, when that's the case, then you know that B is absolutely perpendicular to that plane because it's parallel to dA, which is perpendicular to that plane. Okay. Now, there also happens to be the further problem that the area can be a really large area, and it can have a lot of variation, and the magnetic field can have a lot of variation. So the way you deal with that is, one, you divide the area up in little infinitesimal areas, dA, and then you take the B in that little infinitesimal area, dA, and you use that to do the dot product. And then you find the next dA, and you use that to do the dot product, and you add it to the previous dot product. You keep on doing that. Well, that pretty much is the definition of a Riemann sum. So the actual formula for flux, the most general formula for flux, is the integral of B dot dA. Okay. This is not, it doesn't have a circle over it or anything fancy like that. That's because it's not over a closed surface, or in this case, it's not over a, closed surface. It's not over a closed line segment or anything like that. It's just over an area, and any area will do, including like an area that is your window, for instance, that would be fine. So that's what the magnetic flux is. Now, when we look at Faraday's law, we say, well, how did Faraday actually define it? Well, Faraday, as I mentioned to you before, was he was a natural genius, but he had no formal training beyond basic grade school. And for that reason, he had no basic training in mathematics whatsoever. So despite being a genius, he was held back, not unlike Ben Franklin was here in America. But he was still bright enough to put things together where he had concepts of fields existing in space and stuff like that. So he worded it well enough where Maxwell could just read his book later and write them out in equation form. So ultimately what the equation form became was that the induced EMF, and I'm going to leave a space after this equals on purpose, is equal to negative the instantaneous rate of change of the magnetic flux with respect to time. Okay, so that's actually Faraday's law. And of course, that requires calculus. He didn't understand calculus, or didn't, well, he might have actually had some understanding of calculus. He just couldn't use it. But he definitely understood the idea that it was changing in time, and that its change in time is what mattered. We have to add to this, and this is why I left the space, because if there's more than one loop of wire, say, then it turns out if you go one loop of wire, you might get an induced EMF of 1 volt. But if you take the loop of wire and loop it around so it's 3 loops, then you'll get 3 volts. And if you keep on doing that, it gets larger and larger. So what I'll do is I'll mark in here, but I'll put it in a different color so you know that it's not necessarily in there. You're only going to use it when the loop of current carrying wire or whatever it is you're using has more than 1 loop. So that's Faraday's law. Now, we're going to do some other stuff with that left-hand side a little bit later, but right now that's all we need to know. So for instance, you might want to say, well, actually, let me step back for a second and remind you something about flux. So let's imagine for a second that we have an area, let's say this little area right here. And only that area right there has it, but it in fact has a magnetic field in that little region right there. And of course, these dots in the middle of circles are like you're looking at the end of an arrow, not unlike an arrow you'd shoot, on Game of Thrones or something. But that's basically the head of a magnetic field vector. So the vectors are actually pointing out of the page in this case, and it only covers this little area, which I'm going to call A1. Now, let's calculate, for instance, the flux over A2. Now, how I'm going to draw A2 is going to include A1. And this is going to be A2. So if I want to know the magnetic flux over A2, I'm going to take the integral over A2 of B dot dA. Well, when you go to do that, what you see is there's basically a magnetic field that exists inside of there. Let's say that is BA. That magnetic field actually exists inside that little area. So I'm going to have to integrate over A1 of BA dot dA. But now I've got to integrate over the rest of the area A2, And I'm just going to conceptually call that A2 minus A1. You know, it's not a literal subtraction, but geometrically, I think you can picture that, oh, this is basically a rectangular area with a small rectangular hole taken out of it. And that's what I mean. So in other words, everywhere that's not in A2, but happens to be in A1, or excuse me, that's not in A1, but happens to be in A2 is what we're integrating over in the second integral. And that integral is 0.dA. So that's what the process goes through when you go to calculate something like a magnetic flux, is you've got to evaluate the magnetic field B at each little differential area element. So all the little differential area elements in A1 get B sub A as their magnetic field. But once you get to a differential area element that is still in A2, but not part of A1, then there's no magnetic field there. Or more specifically, the magnetic field strength is 0. So when you take the dot product of 0 with anything, you're going to get 0. So ultimately, it just becomes BA times the actual area A1. Okay, so that's an important thing to consider, especially as we move forward with calculating flux to use in an effort to determine the inductance, which is a new sort of like resistance, a new concept that's going to come after this chapter. Anybody have any questions on that particular example? All right, so that's what the flux is when you have a magnetic field in one particular part and you're actually considering the flux over a huge part that includes that little part. Okay. Now, another example we want to do is we would like to consider a scenario like this. So this was example 1. Now I'm going to do example 2. So with this example, I want to give you an idea of how you can at least physically approximate what a magnetic flux is and therefore an induced current. So what we're going to do is we're going to imagine a loop of wire. Let's make it a square wire. Okay. And the loop of wire, in fact, is going to look like this. Okay. Now this side and this side are both L equals, let's call it 10.0 centimeters, like that. Okay. So it's a rectangular, actually it's a perfectly square loop. It's just drawn in a 3-dimensional perspective. And what we're going to do is we're going to imagine there exists a magnetic field that is perfectly perpendicular to it, and in fact is uniform, so it fills up the entire space. Something like that. And that magnetic field will be called B. Okay. And let's say that the magnetic field strength is going to be 0.200 Tesla. And what I'd like to do is consider A, that's the part that we're doing right now, is when the actual area is perpendicular to the magnetic field. And then we're going to consider part B, when the actual loop, if you will, has now been tilted quite a bit. Well, that last line got kind of wonky. So now it's tilted quite a bit. We still have the magnetic field pointing straight up. But because of this tilt, there's an angle with respect to it. And in fact, that angle you can call this the dA vector. And then this angle right here is about theta equals 30.0 degrees. So what I want to know is the flux for part A and the flux for part B. And then after that, I'm going to say it flips the loop. Whoa, put a P in there. Flips from A to B in 0.010 seconds. What is the E induced? And if the R of the wire is 0.020 ohms, what is I induced? Okay. So that's what we're trying to figure out here. So we can do that. It's pretty easy. First off, I'm going to do part A. So let's use blue to write our solution. So part A, we know that basically the flux, in this case, since the magnetic field is uniform and the area is uniform and the actual angle of the vector is 0 with the dA. In other words, dA, which points vertical in that first case, dA is parallel to B. So that tells us that this is just B times A, which is in fact 0.020 Tesla times L squared, which is 0.100 meters squared. And of course, that's 0.02 times 1/10 times 1/10. That's 0.00020. And that comes out to a unit of Tesla meters squared, which we actually call a Weber. So it's also equal to 0.00020 Webers. That's a WB. Any questions on that first part? Now, part B is only moderately harder. In this case, the only difference is the magnetic field, again, is the same. So that's not a difference. The magnetic field is uniform, so you still don't have to integrate. The only difference is the area has been tilted so that now the dA vector, which is perpendicular to the area, it actually makes an angle of 30 degrees with the magnetic field. So now the flux is going to be B times A times cosine theta, which is what I called it on the diagram. So that's going to be 0.020 Tesla times 0.100 meters squared times cosine 30.0 degrees. And I'll circle off that answer in a second. So when I go to calculate that cosine of 30 degrees, I think is 0.866 if I remember correctly. But we'll work it out. 0.02 times 0.1 times 0.1 times cosine 30. And that gives me 1.732. 1.732 times 10 to the negative fourth. Webers. Okay, so I'm going to circle this answer. And notice that would be 2 times 10 to the negative fourth as well. And this is 1.73 times 10 to the negative fourth. But you see that clearly the flux has in fact changed. So in principle, what you're supposed to do is you're supposed to exactly determine by how much it changes over an infinitesimal amount, and you keep making the time interval smaller and smaller until you find basically the quotient delta phi over delta t being a constant. Once you've gotten that delta t small enough that the next 2 or 3 calculations in a row give you the same digits, at least to the number of digits that you want, then you know you've gone far enough and you've basically implemented a calculus derivative without using, in some sense, calculus. So that's what we're doing here. And that's part of the advantage of the fact that I told you guys it moved in 0.01 seconds. That's 100th of a second. That's a pretty small time interval. So what we know is E induced is the induced EMF is equal to negative N d phi over dt. But you could also say that's approximately equal to negative N delta phi over delta t. So I explained to you that in principle, what you do is try to figure out how much it changes over, say, 100th of a second, and you do a division and all that stuff, and you get an answer. And let's say you want 3 sig figs. If you make it go from 100th of a second to say 5 thousandths of a second or something like that, and the 3 sig figs don't change, then you've gone small enough. But if if one or more of the 3 sig figs change in going from 100th of a second to 5 1,000ths of a second, then you haven't gotten small enough. So you need to keep doing that over and over again. So now we can go ahead and calculate for part C that E induced is approximately equal to, and now I only care about the magnitude. That negative is absolutely essential. If I ever go to plug Faraday's law into some other equation, I absolutely need that negative. But when we're just trying to calculate a flux and all that stuff, I can sort of think of that negative as just helping me figure out or reminding me to apply Lenz's law so I can figure out which direction the current will be. And I can just drop that negative and any other negatives that appear, as long as they're always just multiplying, because ultimately I'm just going to want a positive answer. So what I'm going to do is I'm going to say that it's approximately equal to the change in flux divided by the change in time. And I'm going to say that was in fact 2.0 times 10 to the negative fourth Webers minus 1.73. I think I had 732, didn't I? Yeah, 1.732 times 10 to the negative fourth Webers. And all that happened in the time interval was 0.010. Now we know from doing that, doing the multiplication of 0.02 times 0.1 times cosine of 30, we know we really only have, actually we had 3 sig figs. So we really should have 3 sig figs here. That means only this 2 is not a sig fig. And the other one, when we got 2, that was also supposed to be 3 sig figs. So technically I can have another 0 in here as well. They actually line up in the same place as being a power of 10 to the negative fourth. So that works to having 2 decimal places when we write 10 to the negative fourth power. So what I'm going to do is I'm going to take 2 minus 1.732. Whoa. 732. And of course, that's going to give me 0.268 times 10 to the negative fourth Webers divided by 0.010. And I think that might be where I limited to 2 sig figs. Yeah, that was right. That was what I was limited to. So here's where the 2 sig figs come in. And in fact, I can see already that that's 8 is a is not a sig fig. So I'm going to take this 0.268 times 10 to the negative fourth. And divide it by 0.01. And that's going to give me 2.68 times 10 to the negative 3. Now that's 10 to the negative 3 volts because a Weber per second is 1 volt. Okay. So that's just another sign or another unit conversion you might want to know just in terms of using Webers from now and then, every now and again. So we've now calculated the induced EMF. So I'm going to put a box around that. And I'm going to say this is E induced. Now we know that Ohm's law is actually in play. So E induced, which is really just a fancy word, electromotive force for voltage, must obey Ohm's law. So that's I induced times the resistance. So that means I induced is actually going to be equal to E induced divided by R. And that is, of course, 2.68 times 10 to the negative third volts divided by 0.020 ohms. So we get I induced is equal to 0.134 or 0.134 amps, which is also equal to 134 milliamps. So that's a pretty straightforward calculation of using Faraday's law, calculating induced current, calculating induced voltage, that sort of thing. Anybody have any questions on that? Now, what I want to do is I want to look at these two diagrams, this A and B in example 2, and try to estimate or get an idea of which way the induced current will act. I would like y'all to do the same thing. So first take a look at this and see if you can tell me using Lenz's law in which way will the current be induced. Now remember, this side back here is far away from us. And this side up here is close to us. So all we have to do is show that the current in the front is going to the left or right. And that actually lets us figure out which direction the current's going. So can anybody first tell me which direction the current in that front wire is going as it changes from A to B, the induced current, that is?
In the theta hat direction?
In the theta hat direction, that's probably right, because I suspect you're picturing the XYZ coordinate system in the exact same way I am, which would be X is pointing to the right, or actually you might say even X is pointing out of the page, Y is pointing to the right, and Z is up, in which case, yeah, that would be in the theta hat direction. Or also, just in case someone's not seeing that way, that should mean that the current as seen at the front wire should be going to the right. So what I'll say is I'll start another color because I can. I'm going to say the current is actually going that way. Okay, so that means back here, it's going this way. Here it's going into the page, and right here it's coming out of the page. Okay, and that is sort of a theta hat direction, like you were saying. And the reason I know that is, look, the answer came about because I first realized that the flux was decreasing. The flux is decreasing because the cosine 30 forced it to go from cosine of 0, which is 1 times BA, to cosine of 30, which is smaller than 1 times BA. Therefore, it's going to try to create more of a magnetic field sticking out in the direction of DA. And the only way it can create a magnetic field sticking in the direction that I drew DA there is by going around in the direction that the green arrow is suggested. So yes, that is the direction of the induced current. Anybody have any questions on that?
For A, would there not be an induced current?
A is sort of like a snapshot, and technically so is B. But if we assumed it went from A to B, and in fact that it was going, well, if it started right there, then you wouldn't have any induced. But in all the points from the instant at A, from a split second thereafter, all the way up till it got to B, there would always be an induced current. Just at that split second, there wouldn't be one. If you were imagining that the actual, let me kill the share screen for a second and get it back on the camera. If you imagine for a second that the little rectangle, or the square, if you will, is like this, and it's actually rotating this way with the magnetic field pointing up, and then when it gets right here, it's in position A, and then when it gets right here, it's in position B, well, then you have a different scenario, because in this position, the magnetic field is pointing up, and the angle is in fact probably close to like 30 degrees. So the flux is actually decreasing from here to here. And in that case, it would make the current go around this way, which is sort of the same direction it's going, because it's trying to restore that magnetic field. So it would in fact be going, the part that's closest to me would be seeing current going to the right. And as it got to here, it would continue to go to the right all the way through there. So yeah, I just had to make sure I worked out the details of a split second before we got to position A. Anybody have any questions on that? All right, I'm gonna go back and share screen again, because we have more problems to do, of course. So make sure you work on how to use Lenz's law to find the direction of induced currents and that sort of thing. Other than that, we're going to have some problems just trying to actually apply the equations. And that's what I'm working on now, is going to give you some examples of actually applying equations. So let's imagine for a second that we have a fairly uniform magnetic field. So I'm going to say this will be example 3. And what I'm going to do is I'm going to have magnetic fields pointing into the page. And it's going to extend right up to this this rightmost edge that I just ran into. Right there. So the magnetic field only exists to the left of this line right here. And in fact, the magnetic field is a constant equal to 0.700 Tesla. Okay.
Real quick,
Yes.
I don't see anything. The screen's black for me.
Oh, is that the same thing for everybody?
No,
Can
I'm
anybody
able
else
to
see the screen?
I'm able to see it.
Yeah, I don't know what's going on with you then, bud.
All right, I'll leave and come back then.
Yeah, try that. He's not going to miss too much while we're gone. Plus, it's on video. So now what I'm going to do is have you imagine that there's actually a wire of a certain number of turns, and that wire is going to be pulled out of the magnetic field. And from that, I'm going to calculate the induced EMF. I thought that's what I was going to do. Hold on here. I'd be losing my stuff here. Hold on. Yeah. Okay. So now I'm going to draw a rectangular. That's John coming back now. Good. John, you didn't miss anything. You got lucky. Actually, can't hear you yet, so I'll wait.
I can see now.
Okay. Got it. Well, you didn't miss anything. I was actually using the time to try to figure out where the poop I was. So I got that worked out, and I'm feeling pretty confident now. All right. So I'm not doing that one, not doing that. I'm actually scrolling through my notes and also the book to see what I wanted to show you guys. So I'm going to try to pull this coil from a magnetic field. What I have is the coil is going to be this black wire. It's basically in the shape of a rectangle. Okay. Actually, let's make it the shape of a square. So I'm going to say L is this dimension, and I'm going to say L is this dimension, and I'm going to say that L is equal to 10.0 centimeters. So I'm trying to get 3 sig figs on everything. I'm going to say N, the number of loops, is 100. And I'll say 100 points so we can pretend like that's 3 sig figs. By the way, in case y'all running into any problems with Giancoli, his wording, like if he says a number is 100, he wants to know how many sig figs there are. That question may pop up in your practice test, by the way. We, without that decimal point, and what I taught you, would say without the decimal point, it has 1 sig fig. With the decimal point that I just wrote, it has 3. What he's calling that, according to the way he's interpreting it, is he's calling that an ambiguous number of sig figs. And I don't mind that. I just let you know in case y'all run across that question in any of your tests. So just keep that in mind. Now, what I'm going to do is I'm going to say that this particular rectangular, or actually square coil of 100 loops of wire is going to be pulled out of the magnetic field. And what I want to know is the rate of change of flux. And I want to know the induced EMF, the induced current, how much energy is dissipated, and what force it took. So I'm going to say it did all of this. In other words, we were able to pull it completely out, and I'm going to say delta T is equal to 0. I think I'll say 0.0500 seconds. Okay. So what happened was, I'm going to try to draw this sort of in an animation. So at the end, it has traveled a distance L. And that is basically what we're seeing here, is the coil has moved all the way to there. And the amount of time it took was delta T to get from there to there. Okay. So what I have to do is calculate the flux before and after. So I'm going to say solution. And again, I'll remind you, delta phi is question mark. That'll be part A. E induced is question mark, and I induced is question mark. I'm going to assume the wire actually has a resistance of, I think I'm going to do 0.02 or something like that for my, well, it's 100 loops. Let's say the resistance of the wire R is going to be 10.0 ohms. Okay, so I want to know E induced and I induced. That is part B. And I want to know the energy dissipated. So that's part C. E is question mark. And then part D, I want to know the average force. I'll put a bar over it like that. I know that looks like a vector arrow because I initially drew a vector arrow, but anyways. So here's the solution. First off, I'm going to say flux. Whoa. I'm going to say the flux at T equals 0 is actually just equal to B times A, which I think you can see is 0.7 times 0.1 times 0.1. So that'd be 0.00. I think that's it. And then a 7. So it'd be 0.7, 0.07, 0.07. Yes. And that's Webers. Now, the phi at T equals delta T is of course equal to 0 times A, which is 0. Does everybody see why the flux is 0 at delta T? Anybody not see that? Okay, so I'm assuming everybody gets that. So what I'm going to say is my delta flux, which is what part A is asking for. So our delta flux is supposed to be final minus initial. So in theory, it should be 0 Webers minus 0.007 Webers, which should equal negative 0.007 Webers. Okay, so that should be the answer to part A. Now, I'm going to double check. I did all that with my brain and you know how I am with arithmetic. So I'm going to do 0.1 times 0.1 times 0.7 just to double check, make sure I didn't screw up. And yeah, that was right. That's 0.007. And of course, it actually has 3 sig figs. So technically, I should really be putting 0, 0 after that because they are sig figs. So I'll just mark that way. Now, what is the induced EMF? Well, that's part B for us. So part B, E induced is equal to negative N. In this case, I'm going to say approximately delta phi over delta T, which is approximately negative 100 times negative 0.00700 Webers divided by 0.0500 seconds. So we get E induced. Notice this time I left all the negatives in because I happened to recall that they were all going to cancel out and give me a positive. That's why I didn't worry about it. So anyways, I'm basically going to take 0.007. I'm going to divide that by 0.05. That gives me 0.14. And now I'm going to multiply that by 100 because it's 100 turns. And that gives me 14.0 Webers per second, which is volts. So I'll put 14.00 volts. And I'm just reiterating that we have, in fact, 3 sig figs. That's why I went ahead and wrote a 4th one there. So we would know when we look back at our notes why I put these 2 zeros right here. All right, so we got that. Now we also know from Ohm's law that E induced is equal to I induced times R. So all I got to do now is to calculate I induced. I just divide ooh, wrong color. I divide E induced by R. And that gives me I induced. So I'll say I induced is equal to 14.00 volts over, and what did I end up choosing? Oh, I chose 10 ohms for the resistance of my wire, which actually is quite a lot of ohms, to be honest with you, even for 100 turns. But anyways, when I divide 14 by 10, I get 1.4. So I got 1.40 amps. That's a pretty big current to be allowed. It just said somebody was trying to get in, but I don't see them. Maybe they just, there it is. Okay, so that's the induced current. Everybody cool with this? Understand what's going on? Anybody have any questions about any of this? Okay, looks like no one does. So that's good. All right, so if I want to calculate the actual energy pulled out of this, I'm going to say example 3 continued. If I'm going to calculate the actual energy loss, I know that energy is equal to power times time, specifically because power is defined to be dW over dt, which sometimes we write that as dE over dt. Any of that is all fair game. I don't need to be writing this in red, but I did. So, oh well. So I know that the energy loss would be power times time. And I know that power is, I can say P equals IV, or I can use Ohm's law again. Actually, let's get rid of that. I can use Ohm's law again and say that V is equal to IR. So that's I squared times R. That would be another version we could use. Either one, it doesn't matter. Basically, what I'm going to do is I'm going to find that the current induced squared times the resistance will actually give me the power that's been basically made by this induction process. And when I multiply that by the time taken, which is how long it took to pull it out of the magnetic field, then that'll give me the actual energy. So I'm going to say energy is equal to I squared R times, instead of T, I'm going to say times delta T, because that's what I called that variable. So we found that the actual amperage was 1.4 amps. And it actually has 3 sig figs. So I went ahead and put that 0 in there. That's going to be squared. And then I'm going to multiply that by 10 ohms. And then I'm going to multiply that by the time taken, which I think was 0.05 seconds. Yes. 0.0500 seconds, which is 3 sig figs. I hate dealing with sig figs, but I, try to keep y'all abreast of what the right number is with sig fig rules. So I'm going to do 1.4 squared times 10 times 0.05, and that gives me 0.98. And since we have 3 sig figs, I'm going to call that 0.980, and that is actually joules. If anybody can confirm that with me, please let me know. That'd be great. This, I think, was part C. Yes, I called that part C. So I'm going to put a little C here. So we've now got the energy. Now the energy, remember, is essentially the work done. So we can now take for part D and say energy is actually equal to work done, which if we take it as average, that's just the average force times the delta X, the distance traveled. So what that means is the average force is just going to be the energy divided by the delta X. Well, the energy is 0.980 joules. And the delta X is actually L, which is 0.100 meters. In other words, 10 centimeters. So that's actually 9.80 newtons is the force. Any questions on that? Now, this is very much like an example in your book, so you can look at that. That'll be entirely different set of numbers and stuff like that. As always, the bare minimum for you guys to survive in this class, as well as in 241, which you already did finish, is that you can complete the examples in the book. So you definitely want to go through chapter 29, for instance, and make sure you can do each example. Now, the first time around might be you just reading the example and trying to make sense of it, but then you should be able to come back later, read the example, and then with a piece of paper, cover up the solution and work it out yourself. If you can't do that, you're probably not getting it yet. So make sure you keep doing that as sort of a minimal holy grail, if you will. So anybody have any questions on that?
No.
All right. Well, we could actually look at this force another way too, by the way. We can think about the force as being basically the force required to move a current carrying wire through an actual distance, through a magnetic field, because the very existence of a magnetic field applies a force to a current according to the equation. Make sure I'm using the right color marker and not an eraser. If you remember, we had something along the lines of dF is equal to I dl cross B. That was the F equals Bill equation that I often call it. Okay. So if you actually wanted to calculate what F could be, in this case, the DL, which is supposed to be parallel to the current, the DL is actually going to be basically just the L, so the 10 centimeters. And then the I is going to be the current, which we said was 1.4 amps. And then the magnetic field is B. And notice that the magnetic field and the current are actually perpendicular to each other. So the L cross B part is just going to be basically just L times B, because it's gonna have a sine, but it's the sine of 90 degrees, and the sine of 90 degrees is 1. The actual magnetic field strength was 0.7 Tesla. So let's give it a try. So if this is the case, we have 0.700 Tesla times 0.100 meters times that's our magnetic field, that's our length, times our current is 1.4 amps. Actually, I should put right 1.40 amps. And then times, now remember, we actually have not one little current carrying wire. We actually have 100 loops of that. So we actually got to multiply this by 100 as well. So when we do this, we're going to get times 100 number of loops. So for this answer, we get 0.7 times 0.1 is 0.07 times 1.4. That's 0.098. So it's looking pretty good. Now I multiply that by 100 and I get 9.8. So there's yet another way we can calculate it. And this is one of those things we love to do in science, is when several things point to the same answer, especially when it's, several different laws of physics or several different sciences. They all point to the same conclusion. That's when scientists start to get really cocky about their predictions. That's not unlike what we have with the ozone depletion. That's not unlike what we had with global warming, or what we actually now call basically global climate change, because the warming, by calling it warming, which is really what it's doing, people got the impression that everything's going to be hotter and that snowstorms and blizzards and stuff would disappear, but it's actually quite opposite. In fact, the global warming can in fact cause even more severe blizzards and an even more severe cold. But when you have, it also applies really well, for instance, in the case of when we first started discovering plate tectonics, and when we first started discovering the theory of evolution, all the different sciences were pointing to the same thing. And from all the different sciences all pointing to the same thing, that's when we got kind of cocky about how good it can be. In this case, it's really a small microcosm, of course, because I used mechanical equations. Basically, energy is the work put into the system, which is F average times delta X. But I also used another branch of physics, which is electricity and magnetism, by using dF equals IdL cross B. So using two entirely different branches of physics, I got the same answer. So that gives me some confidence that I did it correctly. The more of those different branches of physics or different sciences altogether that we can get, the more confident we become with our answer. So any questions on that? All right. Well, we now have another neat scenario that I want to show you. And what that's going to be is a neat little system. What did I do with this one? I had the current pointing out of the page. No, I had the current pointing into the page. I'm going to add the current pointing out of the page for this example. So here comes a new example. This is going to be example 4. In this case, what I'm going to do is I'm going to imagine an actual current coming out of the page. Might have been smarter if I'd taken the time to draw these diagrams before class, huh? Haven't actually gotten savvy enough to be able to do that, because I'd really like to make a lot of animations and stuff, especially for my astronomy classes, but oh well. Someday I'll have as much time to teach as I want to. Okay, so that looks like a fairly uniform magnetic field. What I'm going to do now is put a rail system in. So what I'm going to have is a wire acting like a rail like this. And I'm going to say it's perfectly straight, despite the drawing suggesting otherwise. Okay, and I'm going to say that this length right here is L. And I'm going to I think I'll just call it L, just so we can get a neat new result out of it. Now what I'm going to do is put a little metal rail, if you will, across it. So I'm going to take a little piece of metal, and this is up against a metal rail as well. In other words, the black thing is metal and this green thing is metal. And I'm going to allow this green thing to move with a velocity v. And I'm going to say that the strength of the magnetic field is just B. Okay. Now, what I'd like to do is I would like to calculate things like, what is the induced EMF? What is the induced current? What is the force required to move it? All sorts of neat stuff like that. So let's see what we can do. So first off, I'm going to say, I want to know E induced. Whoa, keep switching to an eraser on me. So A, I want to know E induced B, let's say R is equal to 1.00 ohms. So I induced is equal to question mark. That's what I also want to know. And the other thing I'd like to know is what is the actual force? So C, F, the force required, which I'm going to draw here with a red arrow, F equals question mark. Okay. So what I'm going to do is I'm going to think for a second about, and actually let's not say R equals 100. Let's just say R equals R. That way I can get it all in terms of just variables. That'll be kind of neat. So anything that's written without a question mark by it, you can assume you know. So we know L, we know B, and we know V, the velocity. Okay, so that's what we're pretending we're knowing. So if you think about this at some time t, what you have is basically, got to get my pen back instead of my eraser. What we have is basically this black railing and this green wire right here. So this is at time t. Then this distance right here is obviously v times t. Does that make sense to everyone? That the distance from the left-hand side. See, I'm redrawing this into the rail, the left end of the rail. I'm redrawing that, but I'm drawing it at some time t, whereas this drawing is at t equals 0. So if we allow a little time t to pass by, then our kinematic equations tells us that the green rod will have moved a distance v times t. And of course, we know that this length right here is L. So we can say that the flux at this particular time, phi of t, is actually equal to B times A. And of course, the A vector and B are actually parallel. So the cosine is of 0. So it's going to be just L times V times T. So at any time T, we have the current, or excuse me, the area inside that loop, at least until we run out of a magnetic field, which, you know, could happen towards the end, but we can stop it before then. So at any time t, we're going to have B times L times V times T is the flux. Therefore, I know E induced is, can be calculated. So I'm going to say solution. E induced, this is for part A, E induced is equal to negative N d phi dt. In this case, N does not exist. N is 1, in other words. So we're going to forget about this and just talk about the magnitude. So I'm going to say E induced is actually d phi dt. And I'm going to say the magnitude of that as well in case it comes out negative. And for that, if I take the derivative of BLVT with respect to time, what do I get? What's the derivative of BLVT with respect to time?
Question?
Yeah, I'd asked what was the derivative of BLVT with respect to time. I went ahead and answered it because nobody was answering. So we've got part A is that B times L times V is the induced voltage or induced EMF, if you will. Now, if we assume that the current is R, or excuse me, that the resistance is R, then we know that E induced is equal to I induced times R. So I induced has got to equal E over R, which is obviously BLV over R. So I can now box that off too. And that's part B. Anybody have any questions on that?
Why did we take the absolute value?
Because I only cared about the magnitudes.
Oh, okay.
I was just going to do it on the left-hand side, but the derivative in principle could come out negative. So I went ahead and did it to the right-hand side too, because I just want to know the magnitude. There's no ends in it or anything like that. Good question. Anybody else? Okay, now we can go ahead and calculate part C, which is the force. And the force, we can use F equals Bill, for instance. So dF is equal to I dL cross B. In this case, obviously, L is perpendicular to B. So the cross product just becomes a dL times B. The magnetic field is uniform all along L, and L is this long straight thing. So we're just going to say F is equal to Bill. So I'm going to say F is equal to B times the current. Now we know the current is, or actually, let me write it one more time. F equals Bill. So we know B is the magnetic field. We know I is BLV over R. And then we know L is just L. So ultimately we get B squared, L squared, V over R is the force. Any questions on that? All right, now your book will sort of run this in an extreme sense, and I'll just tell you that it's fair game. If you say that the induced EMF in this rod, this green rod that I've drawn, is B times L times V, then you can also say that a wing of an aircraft whose length is L going through a magnetic field whose that's actually perpendicular to the wing at a speed V is going to get a induced voltage of B times L times V. And you'll see there's an example that they used with just that. So you could actually multiply the length of the airplane wing times the strength of the magnetic field times the strength of times the velocity in the correct units, meters per second, of course. When you do all that, out will pop volts, and you'll find that really even the fastest aircraft that we fly in our atmosphere develop, on the order of 1 volt from end to end. So it's not that big of a deal. That being said, jet fuel is mighty explosive, so you wouldn't really want to have a boo-boo. But anyways, I've essentially covered just about everything I wanted to in this chapter. I have only left, all I have is this idea of a transformer, which I'm going to draw a little pilgrim belt buckle really quickly. And this is the pilgrim belt buckle that you had in your 8th grade play or whatever. And what I'm going to have is a wire coming from the right, wrapping around this belt buckle. And in fact, the voltage in is going to be called VP, and the number of turns there is going to be called NP. And then we're going to have a wire coming out, and the number of turns there is going to be NS. The P stands for primary and the S stands for secondary. and out will come a voltage Vs. Now, according to Ohm's law, Vp is going to be equal to basically negative Np d phi over dt. And similarly, Vs would equal negative Ns d phi dt. Now, if we design this Pilgrim belt buckle just right, then the flux through this belt buckle will be very close to the flux through the other belt buckle. I mean, through the other side of the belt buckle, if you will. Okay. So if that's the case, then the derivatives should be equal. So I'll say the d phi on the top one is the d phi left-hand side, and the bottom one is right-hand side. And for a good design, then d phi left-hand side over dt is equal to d phi right-hand side over dt, so that we get Vp over Np is equal to Vs over Ns. Or another way of writing this is Vs is equal to Ns over Np times Vp. And that's the transformer equation. And basically what it means is if the secondary coil has 10 times as many loops as the primary coil, then the voltage will step up. And it's called a step-up transformer. So Ns greater than Np implies step up. Because they say up and down with respect to voltage, not with respect to current. Now, you also know that Pn, best case scenario, is equal to P out. Okay. For the record, they're about 99% efficient in modern day transformers. But because Pn is equal to P out, even if it's 100% efficient, it's just Pn equals P out. We get IPVP is equal to ISVS. And because of that, we can see that IP is equal to, or let's say IP over IS is equal to VS over VP. So IP over IS is equal to VS over VP is NS over NP. So we now have I secondary is equal to N primary over N secondary times I primary. And that's the other sort of downside of this transformer. So if the voltage actually went up by a factor of 10, the current's in fact going to go down by a factor of 10. But that's actually a good thing, because it turns out that's why we send such high voltage from power station to local substation. That's the last two equations. All I'm going to do to finish up this chapter is maybe show you one example of this, but I'm also going to show you an example where a changing magnetic flux or a changing magnetic field can actually create a current and an electric field. And that's basically the last example, major example anyways, in the book. And basically what they do is they have the head of a north end of a magnet right above the south end of a magnet, or vice versa. And they're very, very close to each other. And then they let the magnetism or the magnetic strength increase as a function of time. And from that, calculate, sort of like we do with Ampere's law, calculate the electric field at distances smaller than the radius of the magnet and distances larger than the radius of the magnet. So if you look in your book at that example and sort of read it over, that will help you prepare for next time. After that, we're going straight into chapter 30. So just look over that example. I'm trying to quickly locate that example number so I can tell you what it is. I'll put it on here. You guys can go ahead and go, of course, but I just want to make sure you have it on here. Oh yes, it's example 29-15. So I'm going to cover example 29-15, and I'm probably going to show you an example using these two equations, the transformer equations as well. So I will see you next time, and I will wait for the last person to leave before I leave in case anybody has any questions.
Mr. Younger,
Yes.
could you go back to the example 3 real quick?
Uh-huh. So example 3, you say?
Yeah. The
This
the
part
power
or the other part?
No, the other part.
Okay.
When you're doing power up there, you did the I squared times R. Why
Right.
didn't we do I times V since we had already derived voltage from the last part?
We could have. I actually, I usually like to use I squared R specifically because what I was just talking about was the transformer equation. And that I squared R is exactly a big part of the reason why we use AC current instead of DC current. AC current is very easy to step up and step down. AC voltage is easy to step up and step down. And what we discover is the resistance of a wire to go, say, a wire going from a power station to a substation just outside of a neighborhood. So, a power plant that's actually, using coal-fired power plant or maybe a hydroelectric power plant. That's a set distance that you got to go, and it's a set type of wire that you have to use. You're probably going to use aluminum because it's cheaper than copper. It's still pretty fairly low resistance, that sort of thing. You got to have it a certain diameter, just basically to carry that much current, so on and so forth. So the R is pretty much locked down from a power company or a power generator up to the substation of a neighborhood. And in fact, you have also the current is locked down because basically every house, if you're just supplying a neighborhood, every house uses a 200 amp service. So you're sort of locked into 200 times the number of houses, and then R locks you in by the distance you are away. So this is the formula that you use to calculate how much power is lost in running that power from the power plant up to the substation. You find out that because of these two transformer equations, the one for V and the one for I, that the one for V, if you step the current up if you step up the voltage a lot, say from 120 to 1.2 million, then you're basically making it 10,000 times the voltage, but you're also decreasing the current by a factor of 10,000. Therefore, that I squared is decreasing by a factor of 10 to the 8th. And therefore, you're losing a lot less power to heat as you run that power from the power plant out to the substation. That's a long expression, but a long explanation, but that's part of the reason I really prefer that I squared R equation. But yeah, if you plug in I equals 1.4 and you plug in the V equals, I think we got 0.14 for the voltage. I can't remember off the top of my head, but I think that's what we got. I'm trying to look for, oh no, we got 14. Is this the same one? Yeah, we got 14 volts. And if we multiply that 14 volts times the 1.4, that gives me P equals IV. Oh, okay. So yeah, that still gave me 19.6 for the actual power. And then I multiply the power times 0.05. And that gave me 0.98. So yeah, it still gives me the same amount of energy. So yeah, absolutely, you can use the IV. I just, like I said, I do like I squared R a little bit more because it's sort of a built-in instruction of why we have those power lines going through country fields so high off the ground.
I appreciate it. I have one more question on the bottom.
Yes.
Example 4, you actually ran the derivative for d over dt. What
Right.
made us what made us do derivative there instead of the other equations we did?
Okay, so in this one, by using a bunch of symbols, I was able to come up with a formulaic expression of the flux, B times L times V times T. So if you actually have a way theoretically or experimentally to work up an actual formula that you can take a derivative of, then by all means, you really should use Faraday's law, which has a derivative in it, as a derivative. It's only when you don't have a nice, easy expression or a functional value of the flux as a function of time that you have to use other means. And that's what I was doing in the other cases. I didn't really have a function. I didn't have even a graph. If I had even a graph of the flux changing in time, which you could probably generate, for instance, let me show you this one. On this one, when that was spinning, if I said it took, 0.02 seconds to go from here to here, then it'd probably take 0.06 seconds to go from here to 90 degrees. And then that means 4 times 0.6 would be 2.4. It'd be about 2.4 seconds would be the period of rotation. I could actually make a sine or cosine type function of phi as a function of time for this thing. Or I could just look at the graph of it spinning at that constant rate, and I would see that that looks like a sine, so I could do a curve fit to make it, or I could just look at it and analyze it on a point by point basis by taking the slope at each point, and that's essentially doing the same thing as calculating a derivative. So basically, I was doing the best I could to make a derivative where I didn't have a function.
Awesome. That's what I was assuming. I just didn't want to make sure I was right. I appreciate it.
Yeah, that's it. Good job.
Thank you.
Joseph or Christina?
I have a question. So for the midterm, how much of a percentage is it for the grade, for the final grade is the midterm? Is that 20%?
Man, that's yeah. So the midterm is 20% and the final is 25%. And I completely forgot I wanted to talk to you guys about that. It's good that you asked though, because now I can put it on the video. I want you guys to know that actually y'all did quite well compared even to my face-to-face class. Y'all had a much better average than I was expecting. I still had some very bad grades. It's, believe it or not, people often get on a midterm. I say people. There's always 1 or 2 students that'll get, literally like a 10 or an 18 or something like that on the midterm. And even then, that's not a deal breaker. That students like that have often still managed to pass my class with a C or a B or something like that. And I wouldn't even bar them from getting an A, even if the mathematics worked out that way. If a student can show to me that they peak appropriately for a comprehensive final exam that really is comprehensive, and they make a really high A, like a 98 or something, unless I've got some reason to think they're cheating, I'm really inclined to help them out by, either at least giving them a B, even though numerically they still have gotten, say, a C or a D or an F. I might even give them an A. So that's part of the deal. But what I wanted to announce to you guys is, one, I've made the tests available so that you can see not only the test questions and the test choices, but also the right answers. And that'll stay available until tomorrow at 11:59 p.m. So ideally, what each of you who are not happy or not 100% happy with your midterm grade, what each of you should do is take this time between now and then to record each of those problems in the test, and then completely redo the test neatly, and the whole test, not just the parts you missed or anything like that. Redo the whole test and turn that in to me a week from tomorrow. And, or maybe since you guys are Tuesday, Thursday, I might say a week from Thursday. But either way, you turn that into me, and I'm going to give you, based on how well you do there, I'm going to give you some fraction of points. Like a student that might have made, say, a 20, maybe I'm going to give them the possibility of earning up to 40 points. Whereas a student that made a 50, maybe I only give them a possibility of getting 20 points. If you got a 50 on it and you were that student that made a 50, then I'm only going to give you 10. But if you made 100 on that retest and you got the 50 originally, then I'm going to give you the full 20. So that's what I'm offering to you guys to help your midterm score. Not only that, if you actually do take the final and do better on the final, I'm willing to drop the midterm exam grade and just let you have the final exam grade. So that's two things I'm offering to help you. But I really want y'all to use this retest, and it's not really a retest, but it's essentially retaking the test. I want you can feel free to work with one another to help one another, because I want you to use this as a learning experience to figure out how to solve those problems that were on your midterm exam. I would much rather you turn in a redone midterm exam that you scored, 5% on, but you've learned how to work all the problems, than you turning in a perfect 100 and not having learned how to work the problems. Okay. So I want you to treat this as a learning chance and do that. So yeah, that's a big deal with the final. A lot of people didn't do so well, or a few people didn't do so well, but I offer that olive branch, if you will.
Yeah, cause my grade, my final grade went down significantly. I was just wondering why, cause it went down, went from like an A to a C. So I was just wondering.
Yeah, it's a huge part. In fact, right now it's counting as 45%. So it's literally almost half your grade.
Oh, okay. I got
Because
you.
it's 20
Thank
plus
you.
25. Yep.
Thank you very much. You have a good day. All right.
You're welcome. You have a good one.